Hi guys, and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and we talk about all things Gen Chem related on this channel. On this video, I'm going to be covering different types of chemical equations that you may see in this Gen Chem class. Let's get started. So in the previous video, we learned about chemical equations and the fact that they actually tell us a lot of information about what's happening as that chemical reaction is occurring. They tell us things like the compounds or elements that are involved, the gas state, and we also learned how to balance the equation. So this video is going to be a really short video just to cover the different types of reactions that you would expect to see in this course. You want to make sure that you can identify these things and think about how you would go about first predicting products if you were to see these patterns occur, and then also ensuring that you could balance your equation. So the first type of reaction that we're going to talk about is called a synthesis reaction. Synthesis reactions are those reactions that start with two individual things, likely an element, and then they come together to form one thing, a compound. And so again, this is showing you a schematic of things, but you would want to also take into account as you're forming these compounds, making sure that you list the more metallic element first, and then think about what subscripts would be necessary based off of the preferred charges. So if A has a preferred charge of X, whatever it could be, B has a preferred charge of Y, make sure you crisscross down and assign your coefficients properly, and then you would go about balancing your equation as needed, watching out for anything like diatomic elements or things of that nature. So an example of a synthesis reaction is shown for you here, where we have something like hydrogen and oxygen reacting with one another to form water, or H2O. In this case, we would put hydrogen first, because again, it's found further left on the periodic table. We assign the preferred charge of +1 and -2 for oxygen, crisscross down to get your subscripts, and then you balance accordingly by placing 2 in the coefficient position before your hydrogen or your oxygen. Again, you can tell this is a synthesis because I see two individual things coming to form one thing. Another example is shown here where we have sodium and chlorine reacting. And now notice, just like above with oxygen, chlorine gas is Cl2, not just Cl, because Cl and chlorine and oxygen both represent diatomic elements. So they have to, when they're by themselves, be Cl2 or O2. But now when we're forming this compound, the NaCl, we don't need to drag the 2 over there, but we think about the charges that sodium and chlorine would have and what subscripts those would dictate. Okay, so just make sure you're paying attention to that. Now, the next equation that we're going to deal with is called a decomposition reaction. Decomposition reactions are those reactions that decompose. And if we break that word down, decompose, it's breaking down, right? And so it's just the opposite of your synthesis reactions. So you're going to start with a compound, as you can see here, and then you're going to produce the individual elements. Remember that when you're dealing with things that are diatomic, you would write those subscripts as necessary. And so an example of a decomposition reaction is shown for you here, where we have aluminum chloride breaking down to aluminum and chlorine. Now again, you start with one single compound. Bear in mind why that 3 is there. It's because aluminum's charge of +3 and chlorine -1 would get us that 3 subscript. When it breaks down, it's going to release aluminum and chlorine by itself, but that chlorine will be Cl2 because it's diatomic. You then adjust the coefficient positions to ensure that you're observing the law of conservation of mass, excuse me. All right, the third is single replacement reactions, or sometimes you may see this as single displacement. It's the same thing. In single replacement or displacement, what you're going to be having is a compound reacting with an element. And you need to pay attention to what that element is, because that element is going to be swapping places or replacing one of the elements in that compound to generate something new. Now, if that element is a metal, then it's going to swap places with the metal or the cation that's found in this compound. And so what you end up producing in this example is C and B coming together. And again, we're listing C first because it's the metallic one. And then we kick out A. And there's something that we would need to take into consideration is this thing called an activity series to truly predict if this would occur. But in theory, if you have a metal there, it should swap places whatever the cation is found. Now, if you have a non-metal in this position, well, then the non-metal is going to swap places, okay, or the anion. And so what you would end up with is, if we started like this, you would end up with A and C coming together, because this is swap places, and then B would be coming out. And making sure that, again, you're balancing the equation. So an example here, sodium fluoride reacting with magnesium to produce magnesium fluoride and sodium. Well, magnesium is a metal, so it's going to swap places or replace the metal or cation there, and then we release the sodium by itself. Again, bear in mind why certain subscripts are present. We know in magnesium fluoride that 2 is necessary because the magnesium would be a +2, fluorine -1, crisscross down, and balance accordingly. However, if you have a single replacement reaction in which that element is a non-metal, like in this case, well, now the 2 non-metals are going to swap places. Okay? And so what we end up getting is magnesium oxide and bromine being released. Again, notice we did not just drag over those subscripts, that 2. There's no 2 behind the oxygen in this case because magnesium is +2, oxygen is 2-, and they would cancel out. If you're still struggling with assigning those charges, go back to my videos in chapter 3, and I cover assigning the charges and predicting the overall compound. All right, and then last but not least, type of reaction you want to be able to recognize is a double replacement reaction. Double replacement or displacement, like we've seen in the earlier example, you can recognize that when you have 2 compounds reacting with one another. And so what happens in that case, the 2 compounds swap partners, they swap ions. So the metals swap positions and you produce 2 new compounds. And so for example, here, if we have something like sodium hydroxide and barium phosphate, well, essentially your sodium represents A, hydroxide represents B, keep that polyatomic ion together. Barium represents C, and phosphate represents D. And so now your A and C will swap places. And so you have sodium and phosphate coming together. And then you have barium and hydroxide coming together. Again, with the balancing, you still will keep those polyatomic ions grouped together and adjust the coefficients as needed. As you're predicting charges or predicting the compounds, as you swap the ions, again, make sure you assign charges. Let me erase that, get that out the way. So make sure, like in the case of sodium phosphate, I'm assigning a charge to both and then crisscross down for that product. I hope this information helped as you try to navigate the different types of chemical reactions that are in general chemistry. Be sure to like, comment, and subscribe, and tune in for more videos. I'll see you guys later.